We'll continue on to the last of our derivative rules. This is another way in which our elementary functions can be combined, and because we know the derivative rules for the elementary functions, we will know the derivative rule for the combination. So it's similar to the product rule and quotient rule in that regard, but in this case we're going to be combining the functions in a way that's not a product or a quotient. It's a different way. It's called function nesting or function composition. We're going to do a couple of examples of particular instances of this rule, and then I'll tell you what the general rule is, called the chain rule. But we'll look at it as three different chain rules as we first go through it. The problem here is we have some stuff that's cubed. If the only thing we had was x cubed, just the letter x cubed, then we'd be in good shape. We'd know how to do a derivative for x cubed. The derivative rule would be 3x squared. So this would be okay as a problem if it were x cubed, but the problem here is that it's not x cubed, it's something more complicated. So I have a bunch of stuff in here that's cubed instead of x. Well, the chain rule says that I should just follow the x cubed rule. So the rule that would have gone with x cubed would have been to bring the exponent 3 out in front, and then to reduce the power by 1. Now I don't change what's inside. Whatever stuff was in there is still in there. But I'm using the cube rule. The rule for x cubed is that the 3 comes down in front and the power gets reduced by 1. Now that's not quite right. The reason this is called the chain rule is that it does actually matter what's inside here. It makes sense that the stuff inside here would affect the answer. So what we have to do is multiply by the derivative of the stuff that's inside. So this is what the chain rule looks like. We're following the normal derivative rule for x cubed, but again with our stuff in here, not x. But then we have to adjust this. This is going to be incorrect. We have to multiply by the derivative of whatever the stuff was inside. So you'll see this stuff that's inside the problem in here twice. Once in the rule as you follow it, and then once being multiplied, as derivatives being multiplied. So this then is 3 times 4x to the 6th plus 2 squared, and the derivative of 4x to the 6th plus 2 is just 24x to the 5th. And so I can simplify it just a tiny bit because I could multiply the 24 and the 3 together, and that'd be 72, and then I can enter that into the computer. So that's what it looks like if we have any power. There's no difference if the stuff had been raised to the 1/2 power or the -3 power. Any power that we had a rule for before, we can still follow the chain rule in the same way. Let's look at the exponential functions. It's very similar. Again, what we would know how to do is if this had been g of x equal 6e to the x, then I'd be in good shape. I could just say, well, the derivative is 6e to the x. It doesn't change anything. The derivative of e to the x is, good grief, the derivative of e to the x is e to the x. So that would be correct if it was just e to the x power, but it's not. It's e to a bunch of stuff, right? So my rule for the chain rule is that I should just follow the normal rule. The normal rule for this is basically don't do anything. So if you have 6e to a bunch of stuff, then you have 6e to the bunch of stuff. But the chain rule says that that's incorrect. I have to multiply by the derivative of the stuff. So the derivative of -5x is -5. That can be multiplied by the 6. So if I go ahead and do the derivative and multiply it in one step, then I'll get the right answer here. So again, I have e to a bunch of stuff, whatever it is. Then when I take the derivative of that, then I follow the regular rule. The regular rule says do nothing. The regular rule for e to the x is just e to the x. But that's incorrect. I have to multiply by whatever the derivative of the stuff was. And then finally, our logarithmic functions. And same idea. I say, well, if that had been 6 log x, then I'd be in good shape. The derivative would just be 6 over x. But I don't have x here, I have a bunch of stuff. And so if I follow this rule would say, well, my 6 is sitting there, and I have 6 over whatever that stuff is. So instead of 6 over x, it's 6 over whatever's in there. But that was what I would get by just following the rule as it is. The chain rule says that's incorrect. I have to multiply by the derivative of the stuff. And so we could finish that problem. So, so generally, if you have the natural log of a bunch of stuff, then the correct derivative rule is to follow the regular derivative rule for log, which would give you 1 over stuff, but then also adjust by multiplying by the derivative of the stuff. And so you can see that in these problems, you have this common idea that you're following the normal derivative rule for what we would consider the outermost function, but then multiplying by the derivative of whatever is in the innermost section. And that's the same thing that happened here. Right? This was 3 times stuff squared times derivative of stuff. So same thing happened all 3 times. And that's the general chain rule. There is a statement of that chain rule in your text that says it in a more abstract way. But from our point of view, when we do these computations, all of our examples will fall into one of these categories. It'll either be a bunch of stuff to a power, it'll be e to a bunch of stuff, or it'll be a log of a bunch of stuff. So if we know that we can deal with each of those 3 things, then we should be able to deal with all the derivatives that are in our course. Now we'll move on to a problem that we have not looked at this week yet. So it's a problem that was similar to something we'd done last week, which is once we find our formula for the derivative, we're going to use it for something. And again, we sort of use these things for applications to remind us what the derivative is measuring, either rate of change or slope of a tangent line. So, so it's the latter that this one is supposed to be reminding us of. So we'll just do the problem. We first have to find the derivative rule. When I see this, I have to decide what kind of rule I'm going to use here. This is a product. It's x times 3 minus x cubed. So if I had to categorize this, I would say it's a product of something there and something there. The cube is not on the whole thing, and so I would not categorize that as just being a bunch of stuff to the 3rd power, because that 3rd power is not on the entire thing. So I have a product. So if I have a product, then the product rule says that I need to take the first thing times the derivative of the second. And again, I'm not going to do it. I'm just going to write down what I'm doing. Plus the second thing times the derivative of the first. Now in this case, thankfully, the derivative of the first here is just 1. Derivative of x is 1. So this part's no problem. This one requires a little extra work. That is 3 minus x cubed, and I'm trying to find the derivative of that. So that falls into the category of the chain rule. That's a bunch of stuff. It's not just x. It's a bunch of stuff to the 3rd power. So if the chain rule says that I should follow the rule for raising something to the 3rd power, which would be this, my exponent 3 comes down front, and then the exponent gets reduced by 1. The chain rule tells us that that is not the correct answer. The correct answer would be that times the derivative of whatever that inside stuff is. We can see that the derivative of 3 minus x is -1, and so the 3 out here times that -1 will give us a -3 times 3 minus x squared. So this this answer up here is the derivative of that 3 minus x cubed part. So when I bring that back down here, I just have to be careful. The x that was here before is still there. I want to lose track of what I'm doing, times the 3 minus x cubed derivative, which I went through some trouble to get that, and so that's here, and I'll put that in parentheses so I don't mess up that minus sign. Minus 3 times 3 minus x squared plus, and I'd already said the derivative of x is 1, So this is just 3 minus x. That's supposed to be 3 minus x cubed. My apologies. That's a 3. Now, there is no need to simplify this thing because we're not even, oh, they actually asked for it. Well, maybe they'll make you simplify it. But in general, to answer this question, I would not simplify this because what it's asking me for requires that I only need the slope of the curve f at x equals 2. So f prime of 2 is all that I really need for this problem. In fact, it might have been sensible just to put this in our calculator and use the calculator estimate for slope to get that answer. Finding the derivative tells you the derivatives everywhere, which is sort of a waste if all you want is the derivative at x equals 2. But at any rate, at x equals 2, that means I'm putting 2 in for x, and so that's 2 times negative 3. Putting 2 in here is 3 minus 2, which is 1 squared. 1 squared is 1. And here, 3 minus 2 is 1 cubed is 1. So I have to be very careful with that. You know, if I had a negative 1 squared, that's 1. Negative 1 cubed is negative 1. I have to be careful with making sure I'm doing the calculation inside and then raising to the power. But in this case, I got 1 each time, so that was lucky. So this is negative 6 plus 1, which is negative 5. So that's my slope. So the equation of my line, remember we used the point slope form of a line where I say I have y minus a y coordinate is equal to the slope times x minus an x coordinate. And so to use this form, I need to know the x and y coordinate of a point that's supposed to be on my line. Well, they tell me an x coordinate that's supposed to be on my line, that's x equals 2. And the question is, what is the y coordinate going to be when x equals 2? Well, that's what this is for. Right? F of x tells you the y coordinates. So f of 2, not f prime of 2. Remember, f prime of 2 tells you the slope when x is 2. F of 2 tells you the y coordinate when x is 2. And that's a pretty easy calculation. I have 2 times 3 minus 2 is 1 cubed. So 2 times 1 is 2. So this will be my equation. I probably am going to have to multiply this out and then add 2 to both sides so that I have an equation that looks like y equals. But if I do that, and I run out of room on this slide, so I'll just let you do it, minus 5 times minus 2 is plus 10, and then 2 will get added, and I'll have y equals minus 5x plus 12. And it's easy to check that that has a slope of negative 5. You can tell looking at it. And it's easy to tell that it goes through the point x equals 2, y equals 2, because we can put 2 in for x and notice that we get 2 out for y. So that's the equation of my tangent line.